Okay, in 1991 AB5, we have a similar type of problem, but it's kind of phrased in a little different way. We don't have a function. We don't even have a graph of a function. But what we do have is we have a table with some properties of the original function, the first derivative, and the second derivative over a number of intervals. And what we are told here that f is a function that is even. Alright, so we should remember what an even function is. An even function is a function that is reflected over the y-axis. So for example, x squared is an even function. Sine x is, cosine of x is also an even function. So that means that whatever happens to the left or to the right of the y-axis will just be a carbon copy of what happens to the left, and vice versa. What happens to the left is a carbon copy of what happens to the right. So we're told that the function is even and that it's continuous, and we have a closed interval from -3 to +3. So we should expect with a closed interval and a continuous function that we're going to be dealing with questions of absolute min and max. The function f and its derivatives have the properties indicated in the table below. Now let's take a look at when x is 0, the first derivative is undefined. The function has a value, but the first derivative is undefined and the second derivative is undefined. So what do you know about the point at x equals 0, y equals 1? Should state that at x equals 0, y equals 1, we have a critical value. Now the fact that the function is that the derivative is undefined there means that, but the function does exist, means that we will either have a vertical tangent or a sharp turn. And so I write that down, that at the point 0, 1 we have a critical value. It's not a place where the derivative is 0. Excuse me. It's not a place where the derivative is 0, but it is a place where the derivative is undefined, and that's enough to make it a critical value. In those cases where you have a critical value but the derivative is not 0, there you will have either a sharp turn or a vertical tangent. Alright, then let's take a look at the interval from 0 to 1. The function is positive. The first derivative is negative, which tells me that the original function is decreasing at that point. And the second derivative is positive, which tells me that it is concave up. So I'm working with concave up but decreasing, and I'm in the positive territory. And so I make a little note like that that tells me that I'm decreasing and I'm concave up and my values are positive there. Second, at x equals 1, I have f of 1 is equal to 0, so the value of the function is 0. And what happens there? The first derivative is 0 and the second derivative is 0. Now, since the derivative is 0 there, it is a critical value, and I know that it is a horizontal tangent. However, because the second derivative is also 0, if you recall, when I have a first derivative 0 and I have a second derivative negative, then I would have a relative maximum. And when I have a first derivative 0 and a second derivative positive, then I would have a relative minimum. But I don't have either of those. I do have a first derivative 0 and have a second derivative 0, which means that it could be a point of inflection, which occurs with the third example there. If you notice the change in concavity in that third one. So chances are at x equals 1, at x equals 1 and y equals 0, I make that change in the point. It's x equals 1, y equals 0, not 0, 0. I have a horizontal tangent line, but I don't have a min or a max, and so I have some kind of stationary value there. Right? And we'll go on from there in the next video to analyze the rest of this table here.